Have you ever just stared at a problem that felt so big, so tangled up, you had literally no idea where to even start? Well, today, we're going to break down a method for tackling exactly those kinds of impossible problems. And we're going to do it by looking at a fascinating story from the very dawn of artificial intelligence.
So let's just kick things off with a question. Look at this thing, a seriously gnarly calculus problem. Could you solve it in your head? Yeah, me neither. But what if a computer program could? Would you call that program intelligent? Just tuck that question away for a bit because it's right at the heart of everything we're about to explore. All right, so we're going to look at how we solve these big, messy problems. Our example? A specific type of calculus called symbolic integration. Now don't worry, this is not a math lesson. We're just using it because it's the perfect model for any challenge that looks completely overwhelming at first. So, what do you do when a problem is just too big to solve in one go? You do what humans are great at, often without even realizing it. You change it. You apply some kind of transformation to turn it into a different and hopefully simpler problem. This whole strategy has a name. It's called problem reduction. You're just chipping away at the complexity, bit by bit, until you're left with pieces you actually can solve. And our guide for this whole process is a program from way back in the 1960s. The dawn age of AI. A grad student named James Slagle built a program that could solve these kinds of calculus problems at the same level as an MIT freshman. What's so cool about this is that it basically gives us a miniature introduction to the entire field of AI. It anticipated decades of research.
Okay, so Slagle's program didn't just throw spaghetti at the wall to see what stuck. It was methodical. It had a very specific set of moves, or transformations, that it could use to break a problem down. And these moves fall into two really distinct categories.
And this distinction is absolutely key. On one side, you have what are called safe transformations. These are the no-brainers. They're the rules that are always a good idea, like splitting the integral of a sum into a sum of integrals. They are guaranteed to simplify the problem. But on the other side, you've got heuristic transformations. Think of these more like educated guesses or clever tricks. They're things like trigonometric substitutions that might make the problem way easier, but there's no guarantee. To be an expert, you really need both. So, with all these potential moves, how on earth does the program keep track of what it's doing? Well, it builds a map. It literally creates a visual map of its own thought process, showing how it's breaking that big problem down into smaller and smaller pieces.
This map is called a goal tree, or sometimes you'll hear it called an and/or tree. At the very top, that's our big impossible problem, the main goal. And every time it makes a move, a new branch grows, creating simpler subproblems or subgoals. So it's not just a linear to-do list, it's this branching, beautiful structure of goals and all the little things needed to achieve them.
Let's look at the first type of branch. This is an AND node. This happens when a safe move, like that sum rule, splits one problem into multiple parts. The key word here is AND. To solve the original problem, you have to solve the first part and the second part, and any other parts. Every single one is mandatory, no skipping.
But then, sometimes you have a choice. This is where an OR node comes in. This happens when one of those heuristic tricks gives you multiple possible ways forward. For instance, you could rewrite a function in a few different ways. You don't need to try all of them. You just need to find one path that actually leads to a solution. Anyone will do.
And that, of course, brings up the million-dollar question. When the program hits one of these OR nodes and it has a bunch of different options, how does it choose? Which path does it take? I mean, what would a smart person do?
You might think it uses some incredibly complex, forward-thinking logic, but Slagle's solution was just wonderfully simple. The program measures something called the depth of functional composition. In plain English, it just counts how many functions are nested inside other functions. It looks at all the options and picks the one that looks the least complicated on the surface. That's it. It's not about intuition, it's just a simple, measurable rule.
Okay, so that's the whole strategy. Build a goal tree, use a mix of safe moves and clever tricks, and when you have a choice, just pick the simplest looking path. So, how well did this actually work, and how much knowledge did this thing really need to pull it off?
The results were, frankly, staggering. They tested the program on 56 of the hardest calculus problems pulled from years of MIT final exams, and it solved 54 of them. 54! The only two it missed were because it was missing two very specific tricks in its toolkit. This wasn't just some cute academic exercise. This was a legitimate expert system. But here is the real shocker. You would think an expert system needs a massive encyclopedic knowledge base, right? Thousands of facts? Look at this. The entire thing ran on a table of just 26 basic integrals, the kind a student would just memorize, plus only 12 safe transformations and 12 heuristic ones. That is the whole shebang.
And this just brilliantly illustrates the core discovery here. Expert-level performance in a really complex field didn't require a vast library of facts. It needed a surprisingly small amount of knowledge, but, and this is the important part, organized inside a powerful problem-solving structure. It's not just what you know, it's about how you use it.
This all points to a much deeper idea, this concept of knowledge about knowledge. To really master any subject, you can ask these exact same questions. What kind of knowledge am I dealing with here? How is it all structured? How is it actually used in practice? And, critically, how much do I really need to know to be effective? Answering these questions, that's the real key to expertise.
So, if the magic of being an expert problem solver can just be broken down into a clear, logical system, what does that do to our whole idea of intelligence? Let's bring it all the way back to that question we started with. Here's the paradox. When we demystify something, when we pull back the curtain and see exactly how the trick is done, our sense of its intelligence just kind of disappears. You've probably felt this, right? A friend solves some super tough problem and you think they're a genius until they explain their steps, and you go, oh, well, yeah, that's obvious. And there's this perfect little anecdote from the time that captures this. A student is shown Sligo's program just effortlessly crushing these difficult problems. His first reaction? Wow, okay, maybe computers can be intelligent. But then, the professor explains exactly how the program works, just like we've done here. And after learning how the magic trick was done, the student completely reversed his opinion. His final conclusion? I take it back. It's not intelligent after all. It does integration the same way I do. I mean, that's the punchline, right? The moment the process looked like his own, the magic was just gone. Which leaves us with this final, really thought-provoking question. If breaking down an intelligent process into simple, logical steps makes it seem, well, not intelligent, then what does that say about our own thinking? Are our own flashes of insight and brilliant ideas just a series of these simple steps happening so fast we don't even notice? What then even is intelligence?